Welcome to the fifth part of the webinar on the EICASLAB demo real-time embedded for BeagleBone Blackboard. We will focus on the third control design phase, the target, and specifically on the hardware-in-the-loop, that we will also call briefly HIL submode. After the RCP control design phase, we can work with the final hardware target. EICASLAB provides a target operative mode allowing to export the control algorithm to the final hardware target that will execute it to control first the simulated plant in hardware-in-the-loop and then the real plant in final validation test submodes. EICASLAB provides the routines to generate the basic software not only for the EICASLAB RCP platform itself, but also for a family of devices or for a specific hardware architecture. In fact, EICASLAB provides the SCG for hardware target feature, meaning automatic code generation for hardware target, aiming at generating the target-dependent source code for a set of preselected targets, such as, in this case, the BeagleBone Blackboard. The EICASLAB target module for BeagleBone enables the code generation for the BeagleBone target and the upload and compiling process on it, in order to have the real-time application to run in the hardware target. Let's now consider the first target submode, the hardware-in-the-loop, which allows to test the control algorithm running on the final hardware target suitably connected with the EICASLAB RCP platform in which the simulated plant is executed. Consider now the system layout in hardware-in-the-loop submode. The simulated plant behavior is computed by the EICASLAB RCP platform using the same model developed in modeling and like real-time simulation. In the system layout, the plant, the missions and the interface blocks work since the project has to simulate the real plant and to communicate with the BeagleBone Black hardware target, where the control runs. In the target operative mode, the control execution takes place in the external hardware target. In the hardware-in-the-loop, the plant is simulated by the EICASLAB RCP platform, so the rotating table emulator is not used. When the demo is in hardware-in-the-loop submode, the ACG for HIL Advanced feature generates the basic software and the application software for the EICASLAB RCP platform in order to perform the hardware-in-the-loop tests. The physical Ethernet interfaces are used to exchange simulated measures and commands between the control code generated by the ACG for hardware target feature and running on the external BeagleBone Black hardware and the code generated by the ACG for HIL feature running on the EICASLAB RCP platform. The hardware-in-the-loop trials are managed by the HIL Manager tool running on the EICASLAB RCP platform, which is equipped with a friendly graphical user interface named HIL Manager GUI, subdivided in a menu toolbar, a control panel, and 6 plotting areas for visualizing during the real-time execution the trends of relevant variables. So, during the trial execution, the plant is simulated by the EICASLAB RCP platform and computes the simulated measures. The user-desired trajectory and the runtime parameters are fixed by the user in the EICASLAB project. Measures and parameters are sent from the EICASLAB RCP platform to the BeagleBone Black hardware as Ethernet packets. The BeagleBone Black hardware runs the control routines and computes the command, and the command is sent back to the EICASLAB RCP platform by the same Ethernet link. For the demonstration, we need, of course, to have a BeagleBone Black board and to connect it to the EICASLAB RCP platform. It is connected through a USB connection for powering on the board, and it has an Ethernet connection used for working on the board through a remote terminal and, above all, for the control data transfer between the board and the EICASLAB RCP platform. Let's come back to the software demonstration. we let the AAG control project in Rapid Control Prototyping operative mode. We now close the project in order to consider the demo configuration menu, which opens the demo configuration window, allowing to edit the networking parameters of the demo. In fact, the use of the demo in target operative mode requires some networking activities between the EICASLAB RCP platform and the BeagleBone Black board. Therefore, the interface parameters must be adapted to suit your LAN configuration. Now click on the Scan button related to the PC IP for viewing all the Ethernet interfaces on the PC side, and select the one sharing the same LAN of the board. By selecting it, the subnet mask field is automatically updated. Then press on the Scan button related to the target IP. For selecting your board IP address, that has to match the subnet mask field. Then you press on the OK button of the demo configuration window and the demo will be automatically updated to suit your network configuration. Now open again the AAG control project that we let in Rapid Control Prototyping operative mode, and to operate in target operative mode, open the Control Design Phase selection window and select the target operative mode. By default, the Hardware-in-the-loop submode is selected. In the system layout, you can see that the processor is assigned to the BeagleBone Black 1 hardware target, which is a BeagleBone Black board. This means that the routines and threads it includes are no more executed by the EICASLAB RCP platform as previously done during the RCP operation, but the code has to be generated, exported, and executed on the external target device. Before generating and transferring the code to the external hardware target, let's check the target settings for exportation. Select the menu Target, Configuration Settings. The target parameter file window gets open. Since we work with the board, we will have to make a login on it. We specify here the username, the host name, which is the IP address we have just selected in the demo configuration window, and a password. Then we also select a destination path, that is the path in which exporting the code in the target. Now enter in the processor block. The processor layout includes 5 blocks. The control block, implementing always the same control function of the other operative modes, representing the application software, and 3 interface blocks that depend on the specific operative mode. Through the Out1P1 interface, the board has to send to the EICASLAB RCP platform the command for the plant. Open this interface and check its data. It is an Ethernet interface of type network, having the role of server and using the UDP protocol. The local IP is the IP address of the target that we have specified in the demo configuration window. We then have to specify a port number for sending data and the remote IP and port number, corresponding to the IP and port number of the receiver, the EICASLAB RCP platform. Then we also have to specify a net mask and a timeout. The other 2 interfaces have similar parameters. Let's come back to the system layout. All the blocks outside the processor run in the RCP platform and communicate with the board. Consider as an example the command send from the board. It is received by the interface represented by the in1 block. Let's open this block. The interface window has the same structure already seen in Rapid Control Prototyping. Just note that the remote IP is the target IP and the remote port number corresponds to the port number indicated in the target interface. Once the target settings are correct, you have to generate the real-time control program. For doing this, open the Global Data window and select the Physical view and the BeagleBone Black 1 target. Then click on the LCG IS plus BS button. The LCG for target window gets opened, allowing you to export the whole real-time software to export to the board. Click on the Export button. You first decide in which directory exporting the code. Then, after a while, a dialog will notify that the LCG is completed. After that, press the Upload button, and the source code will be transferred to the board and compiled to a real-time binary application called bb_exe in the remote export directory. In order to proceed with the HIL trial, we have to compile the project, and a compiling report of the compiling process is shown. Then we have to run the HIL Manager tool. Before starting the HIL trial, we run the already compiled board control program using a remote session on a terminal. So let's open a terminal. We need to log in as root user. Then we can remotely log in to the embedded target using the Secure Shell protocol. We can now move to the remote directory selected for the code transfer. This directory contains the BeagleBone Black 1 directory containing the real-time application bb_exe. So let us run such real-time application. Now the remote control application is running, but it doesn't receive any measure. So the standard output prints a periodical reception timeout. Let's come back to EICASLAB and press on the Start button of the HIL Manager GUI. In such a way, the plant sends measures to the control and the trial really begins. There are no more periodical reception timeout, and the plot areas show in real time a set of significant signals. To terminate the HIL trial, simply click on the Stop button of the HIL Manager tool and stop the remote target application, pressing Ctrl-G on the remote session on the embedded target. As well as for the RCP Manager tool, the automatic generation of a timing performance report in HTML is available, and a set of variables is recorded to be post-analyzed by means of the post tool. This presentation of the HIL submode is finished. In the next webinar we will go on showing the final validation test submode of the target control design phase. Thank you for your attention.